We now move on to moment generating functions. As you might guess from its name, a moment generating function allows you to calculate the moments of a random variable. In fact, the moment generating function, or MGF, is an alternate description equivalent to a PDF or a PMF. For a random variable x, we define the moment generating function as a function phi with a subscript capital X of a parameter s, and it's the expected value of e to the s times x. This probably looks a little weird, so let's do some simple examples. Let's start when x is discrete. In this case, x has a PMF, px of x, and the moment generating function is equal to, just by the standard definition of the expected value of a function, it's the function weighted by the PMF summed over all possible values of x. When x is continuous, it has a PDF fx of x, and in this case, the moment generating function is the integral of the function e to the sx times the PDF of x dx. So the expression for the PMF maybe was a little unfamiliar looking, but this expression for the PDF may look like something you remember. If you think about the density function as if it were a signal, this is the Laplace transform of the signal, which is the PDF. In essence, a moment generating function is just a Laplace transform of a PDF. So the moment generating function has its name because it enables you to calculate moments of a random variable. Specifically, you can calculate the nth moment by taking n derivatives of the moment generating function and then setting s equals to 0. To get a feeling for this, let's start with the case where n equals 0. On the left side, we have e of x to the power 0, and on the right side, we have the derivative, the 0th derivative of the moment generating function, ds0, evaluated at s equals 0. But perhaps you don't remember, but the 0th derivative is no derivative at all. So we in fact have the moment generating function at s equals to 0. And on the left side, we have x to the 0, which is 1. So we have actually e of 1, which of course has to be 1. And on the right side, we have phi x of 0. So the theorem tells us the moment generating function at 0 is always equal to 1. And in some way, we already knew that because phi x of s, the moment generating function, is the expected value of e to the power sx. And if we evaluate this at s equals 0, we get e of e to the 0 times x, which of course is the expected value of e to the 0. And e to the 0 is 1, and the expected value of 1 is 1. This theorem is a little more interesting at n equals 1. At n equals 1, we get the first moment, the expected value of x, and we get that this is the moment generating function as a function of s ds, evaluated at s equal to 0. To see where this comes from, it's better to step back and say, well, here's our definition of the moment generating function, e to the s x. And now if we take a derivative, ds, right, we have d ds of e to the sx. And you have to know a little bit about calculus, but in fact, because this expectation represents an integral of the density function, you can exchange the integration, the expectation, and the derivative, and you get d ds of e to the sx. Now, with respect to the random variable x, it's just a constant with respect to taking a derivative with s. And so we get expected value of x e to the sx. Now, evaluating both sides at s equals 0, over here we have s equals 0. We get this is e to the x, and this term, e to the sx, drops out because at s equals 0, it's just equal to 1. If this exchange of the derivative and the expected value that we made here makes you squeamish, then you should go back and look at the definition in terms of an integral over the PDF of this expected value, and you'll see that you're exchanging an integral with a derivative, and while that isn't always okay, it's generally okay with well-behaved random variables because the area under the curve of the density function integrates to 1. This slide repeats our proof, but here the MGF is explicitly written out as an integral over the density function. And once again, you take a derivative, d ds, of this integral. And what we did was we exchanged this d ds and this integral, and we brought it inside and took the derivative of this function, which is x e to the sx for each value of x. And then evaluating at 0 gives us x times the density function. And of course, that integrates to ex. And you can do this repeatedly and obtain that the nth derivative at 0 is in fact the expected value of x to the n. If you've worked with Laplace transforms before, you'll know that there's a whole bunch of standard signals whose Laplace transforms are known. The same thing happens here in probability. For each of our commonly used random variables with a familiar density function, there is a moment generating function which has also been calculated. And if you use these MGFs a lot, the moment generating functions become familiar to you. So for instance, in this problem, we talk about an exponential random variable x, and we say, oh, its moment generating function is lambda over lambda minus s. In the book, you'll find a whole table of common moment generating functions, of which this is one of them. If you're wondering, though, how hard is it to derive one of these moment generating functions, the answer is it's not really so difficult. So for instance, if x is exponential, then we know its PDF is lambda e to the minus lambda x greater than or equal to 0, 0 otherwise, and the moment generating function is e of e to the sx, and that's equal to the integral 0 to infinity e to the sx lambda e to the minus lambda x dx. And now we factor the lambda out, and we have e to the minus lambda minus sx dx. As long as lambda minus s is strictly greater than 0, this is a convergent integral. And this exponential highlights the fact that typically there's some region of convergence for the variable s for which the moment generating function exists. If s is too big, then e to the sx can blow up too quickly, and the moment generating function might fail to exist. However, all of our well-behaved random variables have the property that there's a region of s's around 0 for which we're assured that the moment generating function exists. In this case, when lambda minus s is greater than 0, or equivalently, s is less than lambda, we have that this integral becomes lambda over minus lambda minus s e to the minus lambda minus sx, 0 to infinity, and this is equal to lambda over minus lambda minus s times 0 minus 1. And the result is exactly what we thought we were going to get, lambda over lambda minus s. What we were told in the beginning is, in fact, the moment generating function. So now we can do the real work of this problem, which is to find the first and second moments of the exponential. So to do this, we could, for instance, find the moments by doing the integral. So for instance, e to the xn will be integral 0 to infinity xn lambda e to the minus lambda x dx. And when n is equal to 1, we have the first moment, and we would have to do this by integration by parts. And if n equals 2, we could indeed do this integral by doing integration by parts twice. Here we'll use the moment generating function, and so we have the e to the x is the derivative of the moment generating function, a value at s equals to 0. So it's d ds of lambda over lambda minus s. And we're going to evaluate at 0, but let's first take the derivative. And this is equal to uh, minus lambda over lambda minus s squared times the derivative of lambda minus s, which is minus 1. So it's lambda over lambda minus s squared. Now evaluating at s equals 0, we get 1 over lambda, which indeed is exactly what we've already known to be the expected value of the exponential. We can do a second step by taking another derivative, ds squared evaluated at s equals to 0. And so this is the derivative of lambda over lambda minus s squared. And this equals 2 lambda over lambda minus s cubed evaluated at s equals to 0, which is equal to 2 over lambda squared. This is also a result we knew because you probably remember that the variance of x has to be e of x squared minus e of x quantity squared, and we obtain now 2 lambda squared minus 1 over lambda squared. We obtain 1 over lambda squared for the variance, which is the familiar result you probably also have memorized for an earlier exam. If you keep doing this, eventually you get to the nth derivative, which will be n factorial lambda over lambda minus s to the power n plus 1. And evaluate at s equals to 0, you get the nth moment of the exponential, which is indeed n factorial over lambda to the n. Like other Laplace transforms, the moment generating function has a lot of nice standard properties. One of these is that if we form a new random variable y, which is ax plus b, we can simply write down the moment generating function of y as a function of the moment generating function of x at as and times e to the sb. It's pretty simple. The proof of this comes straight from the definition. The moment generating function of y is equal to e to the sy, but y is ax plus b. So you plug this in and you see that you have an e to the sb that you can factor out. And you're left with the expected value of e to the as times x. And this is the moment generating function of x, but evaluated at as instead of at s. So here we are looking at the quiz for this section, which means we finished it. So far, it maybe hasn't been all that satisfying, but what we'll see is that the moment generating function will be really useful when we look at sums of independent random variables. If you feel like you need more practice with these MGFs, this is a good example because it shows how the same moment generating function works for a discrete random variable. In particular, K has this uniform PMF from 0 to 4. And so we can write that phi K of S is equal to E to the sk, and this is equal to summation k equals 0 to 4, the PMF 0.2 times e to the sk. And so this is equal to 0.2 times e to the s0 plus e to the s times 1 plus e to the 2s plus e to the 3s plus e to the 4s. So we have it's equal to 1/5, 1 plus e to the s plus e to the 2s plus e to the 3s plus e to the 4s. And so if we use this to find the first moment, right, then we can say, well, e of k is equal to the derivative of the moment generating function, a value at s equals to 0. And the derivative is simple because each e to the something s has a simple derivative. So the derivative of 1 is 0 plus e to the s plus 2e to the 2s plus 3e to the 3s plus 4e to the 4s. And now we're going to evaluate that at s equals 0. And we get 1/5 times 1 plus 2 plus 3 plus 4. And and this toy problem shows you how this taking the derivative of the moment generating function of a discrete random variable gives you the moment. So you could have easily looked at this PMF and written down this answer as the expected value of k. But that isn't really the point of this problem. The point of this problem was to show how this derivative of the moment generating function kind of does this for you. And of course, if you take more derivatives uh, and set s equal to 0, you get higher order moments. And eventually, for this particular problem, these moments are kind of can be kind of ugly stuff.